I'm Mercurides, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 25. Find the index of the first term of the Fibonacci sequence to contain over 1,000 digits. We've encountered the Fibonacci sequence several times by this point in the challenge. The first two terms of the Fibonacci sequence are, by definition, 1 and 1. Then each subsequent term is defined to be the sum of the previous two. The first few terms, after the base cases, are 2, 3, 5, 8, 13, 21, and so on. There's not a whole lot of magic tricks on this one. There are explicit formulas for calculating the Fibonacci sequence, but we don't really need those today. The numbers we're working with are small enough that we can more or less iterate directly using the definition of the Fibonacci sequence. The only thing of note is that, of course, since we're looking for a 1,000-digit number, we'll need a language with big num support. Let's start out today in Haskell. We can write a very basic recursive Fibonacci calculator like so. We define outright that the first and second Fibonacci numbers are 1, and then we define the remaining ones to be equal to the sum of the prior two. This is the most straightforward adaptation of the mathematical definition, and it's also one of the least efficient ways to write it. On my machine, it takes several seconds to even calculate the 40th Fibonacci number, and that's only a 9-digit number. The reason is that this recursive approach recalculates everything an absurd number of times. If I ask for the 5th Fibonacci number, Haskell will see that it needs to determine the 3rd and 4th Fibonacci numbers in order to calculate it. So we make two recursive calls. To get the 3rd Fibonacci number, we need the 1st and 2nd, which are known values. So the 3rd Fibonacci number is 2. Now to get the 4th, we need the 2nd and 3rd. We actually already have the 3rd, but Haskell doesn't know that right now. It just blindly keeps making recursive calls, so the program ends up repeating all of the work done for the 3 case twice. Now if we ask for the 6th Fibonacci number, we would do the work to get the number 4 twice, once directly and once as part of the number 5 recursive step. If we ask for the 7th, then we double all of the 5 work, and so on. This is an exponential time algorithm, which means that each additional value we want to compute effectively doubles our required computation time. We could do what we've done in JavaScript and Python in the past and introduce a cache parameter. Haskell doesn't have mutable global variables, but we could certainly do some clever monadic threading with the state or st monads to get the same effect. However, in this case, it's easier to just do the recursion a bit differently. Instead of making 2 recursive calls, let's just make 1. We'll keep any state we need as additional arguments instead of results. That is, our new Fibonacci function will take 3 arguments. The first is the number of Fibonacci values left to compute. When this hits 1, we're done. The second and third arguments are the last 2 Fibonacci numbers we calculated, so that we don't ever need to recompute them. When we start our recursive call, we'll pass 1 and 1 as the seed values for the computation. This works and is very efficient. I can calculate thousands of Fibonacci numbers in a matter of seconds with this one. We can make a minor improvement though. Our last 2 parameters are sort of internal state parameters that the caller shouldn't have to worry about. After all, anytime we want to call this function, we're just going to pass 1 and 1 as the final 2 arguments and let the recursion modify them from there. So really, our public function should only take the n value, and we'll invoke a private helper that keeps track of our state. This is much easier for the caller to understand, and it hides any irrelevant details from them. There's nothing special about the name Go here, it's just a common name in Haskell for a local helper function when there isn't anything better to call it. With this, we can basically solve our problem. Let's modify our recursion a bit so we have a different stopping condition. Our goal is to find the first Fibonacci number with at least 1,000 digits. The smallest number with at least 1,000 digits is 10 to the power 999. So we'll start our recursion at the index 1. When we recurse, we'll increase the index so we keep track of where we are in the Fibonacci sequence. Our stopping condition is whenever the value a is greater than or equal to our target value, at which time we'll return the index n. This runs instantaneously and is basically the approach we're going to take this week once we talk about the language we'll be using. And for that language, it's actually perfectly reasonable. But in Haskell, we can do even better. After all, we took a nice, pretty Fibonacci function and added a bunch of additional work to it. Functional programming is supposed to be all about separating concerns into multiple functions that don't interfere with each other. And yet here, we've mashed our entire computation into one superfunction that understands every piece of it. This was our recursive function before we added the extra bits to it. The problem with this function right now is that it only gives us 1 Fibonacci number. We could call this in a loop, but then we're stuck recomputing a bunch of Fibonacci numbers unnecessarily again, since we're not using the previous results like we should be. Instead, let's write a function that produces a list of Fibonacci numbers. All of them. Remember that Haskell is a non-strict language, which means values will, generally speaking, only be evaluated when they're actually required. So there's no rule against constructing a list of infinite length. For instance, this example function will produce an infinite list. If we call it with the argument 0, it will produce a list of all natural numbers starting at 0 and counting up, going forever. Haskell is perfectly capable of representing the idea of this list in memory. If we were to try to, for instance, get the sum of its elements, then the program would hang forever as it tries to compute every element of this infinite list. But we could get the first 10 elements from the list easily. Or we could filter the list and get another infinite list consisting of, say, all the even numbers. As long as we never try to force the entire list, Haskell is just fine. And in fact, we can force the entire list as long as we're okay with a non-terminating program. This will print out numbers. Forever. Or rather, until either we or the heat death of the universe terminates the program. Haskell will happily keep spitting out numbers for the rest of time. This function doesn't terminate, but it's productive. That is, it does something even though it runs forever. We can write a recursive function very similar to our existing one that instead produces all of the Fibonacci numbers in order. We no longer need to keep track of the index. Instead, we just have our two state parameters. The head of our result list is A, and the tail is our recursive call. Then our public caller, called Fibbo, simply invokes go with the seed conditions for our Fibonacci sequence, 1 and 1. Note that the public caller, Fibbo, isn't actually a function at all. Its type is list of integer. It takes no parameters. This is just a value. Since Haskell is a non-strict programming language, the line between a value and a function that takes a trivial or no arguments is basically non-existent. Once we have our infinite list, we just need to find the index of the first element, which is at least 10 to the power 999. Then we print it out, adjusting by 1 since Haskell is a zero-index language, and the Project Euler problem starts counting at 1. This works, and it's much neater. We've split up our concerns into two separate parts. The Fibbo function, well, the Fibbo value, computes all of the Fibonacci numbers. It doesn't care what we're going to do with them, it just gives us the Fibonacci numbers in order forever. Then we use the built-in function findIndex from data.list to identify the one we're looking for. Before we move on, I want to show you one more way to compute the Fibonacci sequence recursively in Haskell. And this is one of the neatest applications of Haskell recursion I've seen. Here it is. No helper functions, no tricks, just a directly recursive value. Let's break down the first few terms and see how this works. First off, for those of you not familiar with Haskell, zipwith does exactly what it sounds like. It takes two lists and pairs off the corresponding elements using the given function. So in this example, we would get a list of 3 elements. The first one is 1 plus 4, or 5, then 2 plus 5, or 7, and finally 3 plus 6, or 9. In principle, Haskell will stop zipping elements when it reaches the end of the shorter of the two lists, but in our case, both inputs are infinite, so we'll never reach the end of anything. Now, let's take another look at our Fibonacci value. Suppose we want to start printing this Fibonacci sequence variable out. We need to identify its elements in order. So first, we need to identify the first element. We look at the definition of the value. Clearly, the first element is 1, since the definition explicitly says that Fibbo is equal to 1 prepended onto some other list. If all we need is the first element, Haskell will stop here. It won't even look at the right-hand side of the colon operator because it already has what it needs. So we know the first element is 1. This is a value, not a function. So Haskell, or at least the most popular Haskell compiler, GHC, will remember this variable's value rather than recomputing it. That is, if we ever need the first element of this list again, we already know it. Now let's identify the second element. To do that, we need the first element of the result of zipwith. In turn, to figure that out, we need the first element of Fibbo and the first element of 0:Fibbo. But we already have both of those. The first element of Fibbo is 1, for the reasons we just discussed. And the first element of 0:Fibbo is obviously 0 because it's the left-hand side of a colon operator. 1 plus 0 is 1, so the second element of our list is 1. Again, GHC will remember this and won't need to recompute it since this is a simple value. Now let's figure out the third element. The third element of Fibbo is the second element of our zipwith invocation. So we need the sum of the second element of Fibbo and the second element of 0:Fibbo. But that's just the first and second elements of Fibbo. So the third element of Fibbo is the sum of the first two elements. The fourth, likewise, will be the sum of the second and third, and so on. That's the definition of the Fibonacci sequence, written in one line using value recursion. Now that we've had a bit of fun in Haskell, it's time to talk about our language of the week. There's no real magic tricks to our Project Euler solution. We'll be calculating Fibonacci numbers in a loop until we hit a 1,000-digit value, and then stopping and printing it out. Semantically, the desired program is quite simple. This is Piet, the first of the Danger Mouse languages we'll be using, but certainly not the last. Piet is a stack-based programming language, which semantically puts it in the class of GolfScript and CJam. But what makes this language unique is its source format. Piet programs are designed to look like abstract art in the style of Piet Mondrian. A Piet program is a PNG image file consisting of 20 different colors. Our code editor of choice today will be GIMP, the GNU image manipulation program. Now, you might think you already know how this language works. You might be thinking, okay, 20 colors and it's stack-based. So each color has an effect on the stack, right? Maybe red is push an element to the stack, green is add two numbers together, and this will be easy. That is not how Piet works. If it was, this would be a relatively boring language with a relatively boring gimmick. If every color simply had a command associated to it, then some colors would get used more than others, and the resulting work of art would be much less interesting. Instead, Piet is based on color shifts. To explain, I'll need to use the color wheel. The Piet programming language uses 20 colors. White and black are treated specially, so we'll get to those in a minute. The remaining 18 colors are organized into this color wheel, consisting of 6 hues and 3 levels of brightness for each hue. The hues are, in order, red, yellow, green, cyan, blue, and magenta, and we'll refer to the brightness values as dark, middle, and light. Piet is a two-dimensional programming language, and as we move through our program, it's not the colors themselves that determine the command we perform, rather, it's the shift in colors from one position to the next. For a concrete example, the addition command in Piet, as one might expect, pops 2 numbers off the stack, adds them, and pushes the result of addition back onto the stack. Addition is performed by moving 1 step clockwise around this wheel with no change to brightness. So if we're leaving a dark red color block and we enter a dark yellow color block, that's an addition command. But we also perform an addition command if we leave a dark yellow color block and enter a dark green color block, or if we leave a light magenta color block and enter a light red block. The multiplication command is indicated by a color change that's clockwise 1 step in hue and 2 steps darker in brightness. That is, if we were in a light red color block, we could transition to a dark yellow color block to perform multiplication. Note that the brightness values wrap around. So if we're in a middle green color block, we can perform multiplication by transitioning to a light cyan, since light is 2 steps darker than middle. For the mathematicians out there, hue can be considered modulo 6, and brightness can be considered modulo 3. Now I've thrown the word color block around a bunch, and that's because Piet does not, generally speaking, operate on individual pixels. Instead, the language operates on blocks of the same color. A Piet program starts in the color block at the top left corner of the screen. A contiguous region of the same color is called a block. The program's direction pointer starts out pointing to the east. So to move to the next block, we look on the easternmost edge of our current block. Then we move to the east from that pixel and jump into the next block. As we do so, we take a note of the hue shift and brightness shift to determine what command to execute. If the block's eastern edge is greater than 1 pixel in size, then we use the direction pointer's codal chooser. The codal chooser is initially facing left, but it can be swapped to the right. That means that in the case of a tie, the direction pointer will take the leftmost pixel relative to the direction it's facing. So in this example, since we're facing east, we'll take the northernmost pixel as a tiebreaker. If the codal chooser was facing right, then we would choose the southernmost pixel instead. To keep things simple today, we'll try to avoid getting into situations where the codal chooser has a semantic effect on the program. That's how commands in the 18 standard colors work. We'll go into all of the specific commands in a minute, but first we need to talk about our 2 special colors, white and black. If we move from a block of one of the standard 18 colors into a white pixel, then the white pixels act as a sort of slippery or icy floor. The direction pointer slides in its current direction along any number of white pixels until it hits one of the standard 18 colors, and then it continues from there. Note that if we transition through white, then we don't perform any commands during the transition. Here, we start in the light red block on the left, transition through white, and slide into the yellow block on the right. If there was no white in the middle, this would be a hue shift of 1 with no brightness shift, which is an addition command. But since we transitioned through white, no command gets executed and we simply continue the program from the light yellow block. So white pixels act as empty space that we can freely travel through. And they can also be used to switch colors without executing any commands, which will be handy in loops when we need the start and end of an iteration to line up neatly. Black pixels, on the other hand, act as walls. If we're trying to traverse through our program and the direction pointer hits a black pixel, it stops where it is and tries to find a way out. First, it swaps the codal chooser, switching how we break ties when exiting a block. If we still end up in a black pixel, we rotate the direction pointer clockwise and try again. This process will repeat up to 4 times, trying every combination of direction pointer and codal chooser, until we end up in a block. If we try all 8 combinations and can't escape the walls, that's the end of the program. In fact, that's the only way to end the program, so trapping the direction pointer in a block surrounded by walls is necessary to correctly terminate a Piet program. The entire source image is implied to be surrounded on the outside by a layer of black pixels, so the edges of the image are treated as walls, just like black pixels are. Since this is a 2-dimensional programming language, looping and control flow will be done by routing our direction pointer back to the same place in our source code. Now, let's talk about the commands available in Piet. There are 6 possible hue shifts, including no shift at all, and there are 3 possible brightness shifts, again including no shift at all, for a total of 18 possible transitions. However, really only 17 of these are possible, since the transition which changes nothing obviously won't occur. That is, there's no way to transition from a block into another block of the same color, since that would require 2 identically colored blocks to be touching each other, and in that case, we don't have 2 blocks at all, just one large one. So there are 17 possible transitions. That makes 17 commands. And this is a stack-based language. Most of the commands are pretty simple. A brightness shift of 1 with no hue shift is the push command. The push command pushes a number onto the stack. Specifically, the push command counts the number of pixels in the block we just came from and pushes that number onto the stack. In this example, we start in a block of 13 middle red pixels, and we move to a block of 9 dark red pixels. The hue hasn't changed, but the brightness has shifted by 1. That means this is a push command. And a push command pushes the size of the origin block. The block we're coming from has 13 pixels in it, so we'll push the number 13 onto the stack. This is the only command that uses the number of pixels in a block to determine its behavior. There's also no direct way to push the number 0 or any negative numbers onto the stack. So if we need numbers which are less than 1, we'll have to compute them by subtracting 2 positive numbers. A brightness shift of 2 with no hue shift is the pop command, which pops the top value off the stack and discards it. A hue shift of 1 with no brightness shift is the addition command we already discussed. Hue 1 and brightness 1 is subtraction, and 1, 2 is multiplication. 2, 0 is division. Note that everything in Piet is an integer, so this performs integer division. 2, 1 is the modulo or remainder operation. 2, 2 is logical negation. For the purposes of this command, 0 is the only falsy value, so logical negation takes 0 to 1 and all other numbers to 0. 3, 0 is the greater than command. This is the only comparison operator we have access to. It pops 2 values and pushes the number 1 onto the stack if the second from the top value is strictly greater than the top value, or 0 otherwise. 3, 1 is the pointer rotate command. It pops 1 value off the stack and rotates the direction pointer clockwise that many times. If the value is negative, then the direction pointer is rotated counterclockwise instead. We'll use this for conditionals. If we have a Boolean value, that is, a value that we know is either 0 or 1, then the pointer rotate command will rotate clockwise once if the Boolean is true, or we'll keep going in the same direction if the Boolean is false. 3, 2 is the codal switch command. It pops 1 value off the stack and switches the codal chooser that many times. The codal chooser only has 2 options, so essentially, if the pop value is odd, then we swap the codal chooser to its other value, and if it's even, we do nothing at all. Like I said, today we're going to avoid relying on the complexities of the codal chooser as much as possible, so we'll mainly use the direction pointer for conditionals and looping. 4, 0 is the duplicate command, which makes a second copy of the value at the top of the stack. 4, 1 is the roll command, which is a bit more involved, and we'll discuss that in a moment. The final 4 commands are centered around input and output. 4, 2 takes a single integer from standard input and pushes it onto the stack. 5, 0 takes a single character as input and pushes its ASCII value onto the stack. 5, 1 pops a value off the stack and prints it out as a number. And 5, 2 pops a value off the stack and prints out the character whose ASCII value is equal to that number. I skipped over the roll command because it's a bit more complex, but it's also going to be incredibly useful, as roll is our general purpose stack shuffling command. Here's how it works. Suppose we have a stack consisting of, from the bottom, 1, 2, 3, 4, 5, 6, 4, and 2. Roll starts by popping 2 values off the stack. The top value is the count, and the second value is the depth. The count determines how many times we're going to perform the roll operation, so in this example we'll perform the operation twice. A single execution of the roll operation is defined as follows. Take the top n values on the stack, where n is the depth argument. Now rotate those values so that the top value ends up buried n deep, and all other values move up 1 position. In this example, after popping our arguments, our stack consists of 1, 2, 3, 4, 5, 6, with 6 on the top. Our depth argument is 4, so we look at the top 4 elements of the stack and rotate them, burying the 6 4 values deep. After just 1 execution of the roll operation, our stack is 1, 2, 6, 3, 4, 5. But our count argument is 2, which means we're doing this twice. The second time, the number 5 is on top, so we bury it just below where we put the 6 a moment ago, and get 1, 2, 5, 6, 3, 4 as our final result. This single operation gives us total control over the stack. We can use the roll command to reorder the stack however we like. If we want a particular value on top, we just roll until it happens. If we want to put a new value somewhere in the middle of the stack, we can push it and then roll it down. Effectively, now that we have the roll command, our value stack is a random access array. Let's make a small Piet program to show how we'll be manipulating the stack. Specifically, we'll write a program to calculate the nth triangular number. The nth triangular number is defined to be the sum of all of the natural numbers from 1 up to and including n. Our program will take 1 input from the user and print out the correct triangular number. We've seen a few clever techniques for computing triangular numbers efficiently, using things like Pascal's triangle or even an explicit formula. But the point of this example is to demonstrate some basic stack manipulation, so we're going to do it naively with a loop. Remember that this is a stack-based language, so I'll be showing the stack as we go. We start the program in the top left corner. Aside from the push command, instructions don't care about the size of a color block, so I'll be keeping color blocks at size 1 unless I need to push a constant greater than 1. First, I'm going to push the number 0. This will live on the bottom of our stack and will serve as our accumulated sum during the loop. We actually don't have a way to push 0 onto the stack, since that would require a color block of size 0. So instead, we'll push the number 1 twice and then subtract. Start with a light red color block. There's no specific reason I chose that color in particular. I just needed a place to start, but any of the 18 standard colors would have worked. Now we want to push the number 1. We've got a source color block of size 1, so to push it onto the stack, we need to shift hue by 0 and brightness by 1. For brevity, I'll be referring to the shifts as ordered pairs of hue shift followed by brightness shift. So the shift we want right now is 0, 1. Our next color block needs to be middle red. Now we want to push 1 again. That's another 0, 1 shift, so we transition to dark red. At this point, we have 2 1s on the stack. Next is the subtract command, which is 1, 1. We need to move 1 in the hue direction and 1 in the brightness direction. We're on the darkest variant of these colors, but remember that brightness wraps around, so our next color is light yellow. Light yellow is 1 darker and 1 hue away from dark red, if you don't think about it too hard. Now we want to get user input. Getting input as a number is 4, 2, so coming from light yellow, that's dark magenta. Now we start our program's main loop. I'm going to put a gap of white here, just so we don't have to worry about making the colors line up when we loop back around to this point. This also delineates our program's sections a little bit better. I'll also put a couple of black pixels next to it. This won't have any actual effect on our program, since the direction pointer will never actually hit those black pixels. Again, it's just to make it a bit clear where the flow of control might be coming from. You can think of it as a sort of comment. The first thing we want to do in our loop is check if our program is done. We're done if the input value, which is at the top of our stack and will also serve as our loop counter, has hit 0. Duplicate the top of the stack. The duplicate command is 4, 0. We're coming from a gap of white, so I can start on any color I choose. We'll start on light blue and transition to light green. Now we want to compare the input against the number 0. We push another 0, which we do using the same push 1, subtract trick as before. Then we compare. Again, I'm putting gaps of white at places in our program that are sort of logical separators. Think of it as like commenting our code and making things a little easier to refactor in the future. All the things a good programmer should be thinking about when making abstract art. The greater than command is 3, 0, so we'll go from middle magenta to middle green. Now at this point, the bottom value on the stack is our accumulated sum, which is 0 on the first iteration. On top of that, we have our loop counter, followed by the result of the comparison. If the top value of the stack is 0, we want to print the result and terminate our program. If the top value of the stack is 1, we want to continue. I'm going to invert this result so that our stopping condition is when the top value of the stack is 1, and our continuing condition is when the top of the stack is 0. Logical negation is 2, 2, which takes us to light blue. Now we execute the pointer command. That's 3, 1, so middle yellow. This pops the top of the stack. If the top value is 0, we continue forward and proceed with our loop. If the top of the stack is 1, we make a clockwise turn into the final steps of our program. We'll get into the clockwise turn case in a minute. Let's assume for the moment that we continue our loop. Again, I'm putting some black pixels here as a note to the reader that program flow might change at this point. In the case that we continue, we want to add the counter value to the accumulator, then decrement the counter and loop again. We need to do 2 things to the counter, so let's duplicate it. Duplicate is 4, 0, so we'll go from middle green to middle red. Now remember when I said we started a loop earlier in this first row? Eventually our program's flow is going to need to get back to that point. So we'll need to start turning back that way at some point. We don't actually have a lot to do inside our loop, so let's go ahead and make the turn. I'm putting a black pixel here. This one actually does have an effect on the program, unlike the last ones. When the direction pointer leaves the middle red color block, it'll hit this wall. At that point, Piet will first try to swap the codal chooser. This will fail to solve the problem, as we're in a white pixel. And besides, I said I was going to try not to rely on the codal chooser much, and instead use the direction pointer. So once that fails, we'll make a clockwise turn and proceed. The clockwise turn will solve our problem, and now we'll be moving south rather than east. At this point, the stack consists of 3 values. On the bottom, we have our accumulated sum. Above that, we have 2 copies of our counter. I'm going to bury the top counter at the bottom of the stack, and I'm going to do it using our roll command. This will be a roll of depth 3 and count 1, and when we're done, the stack will look like this. To do that, we need to push our roll constants. We'll push the number 3, then the number 1, and then execute the roll. Start with a light red color block of size 3. Move to middle red of size 1, then dark red of size 1. Remember that the push command is 0, 1, so this is 2 stack pushes in a row. Now we roll. That's 4, 1, which takes us to light blue. Next, perform a quick add command to sum the top 2 stack elements. Then we'll turn clockwise back toward the start of our loop. We technically only need the bottom black pixel here since we'll always turn clockwise rather than counterclockwise. But the second black pixel makes this a bit more explicit. I want the counter back on top of the stack now. So I want to swap the top 2 stack elements. Unlike GolfScript, Piet doesn't have a dedicated swap command, but we can easily replicate it as a special case of the roll command. Specifically, swapping the top two stack elements is just a roll with depth 2 and count 1. So push 2, then push 1, and roll. Now we want to subtract 1 from the counter. Push 1 and subtract. We're ready to jump back to the beginning of our loop, so we'll just have the direction pointer slide neatly along a trail of white, taking a turn in the middle until we end up back where we started. That's our main loop. Now let's talk about the exit condition for our program. At the point we exit the loop, the top value of the stack is 0 since it was formerly our counter, and the final solution is immediately below it. Pop the top element of the stack, and then pop and print the second from the top. Now we need to terminate our program. The most straightforward way I've found to do that is with a prism that looks like this. We enter this little box. We came from the white pixels, so we don't perform any actions. Now the direction pointer can never escape this box. Regardless of which direction we're facing and what the current value of the codal chooser is, we'll never try to step out through the northern middle pixel. We'll try the eastern side, the western side, both ends of the south wall, and both ends of the north wall, but we'll never actually find an exit, and once we've exhausted our options, we terminate. And this prints out the nth triangular number in Piet. This also shows all the techniques we'll be using in our Project Euler solution. We'll loop by circling back to an older point in our program, we'll roll the stack to access values lower down, and we'll use the exact same box prism to terminate our program at the end. As a reminder, our Project Euler problem asked us to calculate the Fibonacci numbers until we got one that consisted of at least 1,000 digits. Then we'll print out the index of that number and call it a day. A lot of people have written Piet interpreters, but I'll be using our Piet, which has explicit support for big number arithmetic, and we'll definitely need some big numbers today. Our Piet is written in Ruby. Well, more specifically, it's written in JRuby, the Ruby interpreter that runs on the JVM. Let's get started. First, we'll push 3 values onto the stack. We'll push 1, 1, and 2. The pair of 1s represent the previous 2 values in the Fibonacci sequence. The 2 on top indicates the index of the most recent Fibonacci value, which will be incremented on every loop iteration. Now we enter our main loop. The very first thing we'll do is add 1 to our counter. That is, we'll push 1 onto the stack and then add the top 2 stack elements. Now I want to work with our 2 Fibonacci values, so I want to bury our counter at the bottom of the stack. That's a roll with depth 3 and count 1. So push 3, then push 1, then roll. Now we need to generate the next Fibonacci value. Duplicate the top Fibonacci value, then roll it lower down on the stack. Then add the top 2 stack elements. At this point, the top 2 elements of the stack are the most recent 2 Fibonacci numbers, with the top of the stack being the new one we just generated. The third element down on the stack is the index of this new element. Now comes the slightly obnoxious part, and you'll see why it's slightly obnoxious in just a minute. We need to check if we're done. First, duplicate the top of the stack. We want to compare the top of the stack to the number 10 to the 999th power. Well, actually, since our only inequality is strict, we want to compare it to 10 to the 999th power minus 1. The problem is, the only way we can push constants onto the stack is with a block of color that's as big as the given constant. If we want to directly push the number 10 to the 999th power minus 1 to the stack, we'd need 10 to the 999th power minus 1 pixels to do it. Assuming a maximally efficient PNG color palette consisting of only the 20 colors needed for Piet, that's a color depth of 5 bits per pixel. To store 10 to the 999th power minus 1 pixels, we need 5 times that many bits, or 5/8 that many bytes. That's approximately 6.25 times 10 to the 998th power bytes. According to Wolfram Alpha, there are 6 times 10 to the 79th atoms in the universe. If we could save 1 byte to every atom in the universe, we wouldn't even be close to storing our hypothetical PNG file. In fact, if every atom in our universe contained its own universe equal in size to ours, and we stored a byte in every atom of each of these sub-universes, we still wouldn't even be close to being able to save this Piet program. So unless you have a handful of recursively enumerable atomic pocket dimensions lying around, we're going to need a better tactic. Here's what we're going to do. Push the number 10 using 10 pixels, then duplicate it and multiply it. That gets us 100. Now duplicate and multiply again. That gets us 10,000. I'm going to start referring to these using scientific notation now. So this is 10 to the power of 3. Now I want to turn counterclockwise to keep going. I actually can't do that very easily. Piet will always try to turn clockwise, and if that fails, it'll turn clockwise again, resulting in a 180-degree turn going back the way we came. So as the old adage goes, 3 rights make a left. So we'll just turn right 3 times to go left. Now that we've turned, duplicate and multiply. And duplicate and multiply. And duplicate and multiply. Isn't this fun? Now we're at 10 to the 32nd power. Duplicate twice and multiply all of those together. That gets us 10 to the 96th power. Now we're going to push 10 to the 4th power again. We've already done that, so just do the same thing again. Push 10, then do our little duplicate and multiply dance twice. Then multiply one more time to get 10 to the 100th power. Next, duplicate and multiply to get 10 to the 200th power. Now duplicate twice, then multiply once. That leaves 10 to the 400th, followed by 10 to the 200th. Duplicate and multiply the top to get 10 to the 800th. Then multiply the remaining 2 values to get 10 to the 1000th power. Now push 10 and divide, then subtract 1 to get 10 to the 999th minus 1. Now that we've got our target number on the stack, we can do a greater than comparison. And then we execute the pointer command. If the current Fibonacci number is greater than our target, we'll turn clockwise toward the center of our program. If not, then we continue straight ahead and to the west. Assuming we haven't finished our program, we just need to reorganize the stack so we're ready for our next loop iteration. To that end, we'll do a roll of depth 3 and count 2. Push 3, push 2, then roll, and then fall right back into the beginning of our loop and go again. Now, back to the end of our program. If we exited the loop, then the current stack consists of the 2 Fibonacci numbers at the top, followed by the index underneath that. We don't care about the Fibonacci numbers anymore, just the index. So roll the index to the top, print it out, and then trap our poor direction pointer in a prison to end the program. This runs in about 4 seconds and gives us the right answer. Now we've solved Project Euler problem number 25 in Piet. And honestly, about 60% of this program's volume is producing the number 10 to the 999th minus 1. If we didn't have to do that in such a roundabout way, this would be a tiny picture. Regardless, tune in next time when we dive back into the class of POSIX shells with Project Euler problem number 26 in Z shell, a board-derived shell with a focus on customizability.